Whenever bonds are formed or broken in a chemical reaction, energy is transferred. And as a solid dissolves in water, like in this experiment, you have sodium thiosulphate, which is the solute, the crystals, okay? So as it dissolves in water, its bonds are broken and a change in temperature is observed. Now, if energy is absorbed from the solvent by the solute, which is the sodium thiosulphate crystals, the solid gets to dissolve and the system, that is the container, be it the calorimeter, gets colder because the solute absorbs heat from the surrounding to dissolve, and as such it gets colder, which means that the reaction is endothermic and it has a positive enthalpy change. But if energy is released, the system gets warmer, alright? Then the reaction is said to be exothermic and it has a negative enthalpy change. Now, the molar heat of solution of a compound, in this experiment sodium thiosulphate, is the heat transferred when 1 mole of sodium thiosulphate, which is the solute, dissolves in a solvent, which is the still water that we will be employing in this experiment. Now, a calorimeter will be given to you, and essentially calorimetry is a technique we use to measure the amount of heat evolved, that is given out, or heat absorbed in some chemical processes. So we tend to actually conserve all the heat released by carrying out the chemical process, the reaction in the calorimeter, which is the system, right? So, and the calorimeter usually contains a stable liquid, right, that makes good contact thermally with the process, all right, once the solute is being dissolved, okay, and during the investigation, that's during the experiment. So if the process involves heat, that is giving out heat, the heat energy is transferred to the liquid and to the material of the calorimeter. The material of the calorimeter is copper. Most calorimeters are made with copper, or made of copper, okay? In the same way, if heat is absorbed, because essentially in this experiment, heat is going to be absorbed, right? It's a dissolution process, and for a solid to dissolve and become a solution, solute plus solvent gives you solution. So in the same way, if heat is absorbed, the heat energy is transferred from the liquid, that's from the solvent. Remember, you're making use of warm water, all right? So the heat is transferred from the liquid, which is the solvent, and the material of the calorimeter, that is the component of the calorimeter, that is copper, now to the solute, which is the sodium thiosulphate crystals, causing it to dissolve and form a solution. And what that does is that it causes the temperature of the solution to drop. That is essentially what this experiment is all about. So before we go to the procedure, you have to also know that the temperature change before and after the dissolution of the sodium thiosulphate is taken as the difference between the final and initial temperature, which we regard as change in T. So for you to carry out this experiment, you have to also know that the heat transferred in a calorimeter is expressed as this equation. You can see Q, which is also enthalpy change, equals MC change in temperature If you have the mass, C is specific capacity. Okay, so for you to carry out this experiment, you have to measure a given weight of the sodium thiosulphate crystal. You have a given weight, you have to measure, know the weight you'll be using. Okay, you have to note it, then measure the weight of the empty calorimeter. Okay, then you add 100 ml of distilled water. All right, distilled water, warm distilled water, whose temperature is slightly above room temperature. Room temperature is around 23.5. okay, so you have to ensure that the temperature is such that it's just either +5 or +10 in that limit. So you'll be expecting that once you've added the distilled water into the calorimeter suited with a thermometer, the temperature should rise around thereabouts 28, 30, 33 thereabout. That's +5 to 10. Okay, now once you've done this, once you've introduced the warm distilled water into the calorimeter, you allow the temperature to equilibrate. All right, and then you record the temperature of the water. Now you've noted that temperature as θ1, and you don't have to remove the thermometer from the system. Now, next thing you have to do is carefully add pre-weighed finely powdered crystals of sodium thiosulphate. All right, you have to weigh it, know the actual amount you take in. All right, the mass of the sodium thiosulphate you take in. All right, then you carefully add it into the calorimeter to dissolve. All right, you could actually stir it so that it dissolves. So once it has dissolved, record the greatest temperature change observed. So there's going to be a temperature change. In this case, we know that the temperature is going to drop due to absorption of heat by the sodium thiosulphate crystals while dissolving, which is an endothermic process. So you have to know the temperature. So if initially you had the initial temperature at, let's say, 33, you wouldn't expect the next temperature to be higher. Okay, it's going to drop. Okay, it's going to drop, and then the system gets colder because it's an endothermic process, like I've explained earlier. So, and that is that. So basically you need those two temperatures. You need the mass of, looking at it, we're looking at to determine the heat of solution, and the heat due to the dissolution of the sodium thiosulphate. So you would need the specific capacity of copper. That's calorimeter made of copper, is a constant. Okay, and the constant is 0.385 joule per gram degree Celsius. And then you also need the different temperatures. Let's say if your initial temperature was 27, and then after the addition of the sodium thiosulphate crystals and it dropped to right, let's say 20 degrees Celsius, okay, which is endothermic due to the absorption of heat, So, and then you have to also know the mass of sodium thiosulphate that you took. Let's say it was 5 grams. It's very important. You have to note it because you would need it to find the moles of the salt. That's the moles of the sodium thiosulphate, okay, as you can see here. All right, so the next thing you would have to do is to find the heat of solution. What is the heat of solution? That is what you have to find first. Then we have to look at this equation and then remember that heat was absorbed by the calorimeter and heat was also absorbed by the solute, all right, to form a solution. So in this case, we'll have an equation that looks like this, okay, that says, let's say Q equals the mass of calorimeter, which you would have taken at first. Then you have specific heat of the calorimeter, And usually calorimeters are made with copper, so we have a constant which is 0.385, right, joule per gram degree Celsius. Then we have the temperature change. You remember the initial temperature and the final temperature, you have to just do a subtraction there. Then you add it to the heat absorbed by that of the solution. What is the solution? Okay, what's the mass of the solution? Solute plus solvent. Solvent, you measured 100 ml of the distilled water, remember, and then you added, let's say, 5 grams of the sodium thiosulphate crystals. That's going to be 105. Okay, that will be the mass of the solution. Essentially, the density of water is 1. So if you're taking 100 ml of water, that means you're taking 100 grams of water. All right, so that would be 105 grams, for example, if you took 5 grams of the sodium thiosulphate. All right, then you were told to assume that the specific capacity of the what is it called, the sodium thiosulphate crystals should be equivalent to that of water. All right, so that means specific capacity of the solution, you have to take it as 4.184. That's joule per gram degree Celsius. Then multiply by the same temperature change. Then you find your heat of solution. All right, once you've solved arithmetically correctly the value, your units should be in joules. Your units should be in joules. All right, so once you've done that, then you are halfway gone to finding the molar heat of solution for sodium thiosulphate crystals, which is the aim of this experiment. And how do you do that? You have to divide the heat of solution that you've gotten in the previous by the moles of solutes. That's the moles of the sodium thiosulphate crystals you introduced into the calorimeter. So whichever value you got as your heat of solution, divide it by the moles of solid. And how do you get that? All right, what mass did you take? If you took 5 grams, all right, and the molar mass of sodium thiosulphate, you calculate that around 100 and something. So once you've divided those, you would have the moles of solid. So you divide the heat of solution by the moles of solid. Whatever it gives you is in joule per mole. Okay, then you would have to convert it to kilojoule per mole, and that will give you the molar heat of solution. And then that is the enthalpy. And then you were given you were told to, what is it called, you were told to express your answer as a thermochemical equation. There are different ways to do it. You can just write a reaction between the solute and the solvent to give you an aqueous solution. Okay, and then you have to state their chemical state. If it's in liquid, if it's in solid, if it's in the aqueous form, those should be there, well reflected. Then followed by the enthalpy, maybe change in H equals to plus this kilojoule per mole or minus this kilojoule per mole, and that is how you express it. Just have the equation of reaction attached with the enthalpy change for the reaction. Right, so that is how you actually get to carry out this experiment.